So this is probably one of the most common video GIFs you'll see of RFDiffusion. It's pretty much what you'll be doing for the binder design project, where you'll be diffusing a binder towards a very specific epitope. As you can see, it starts with random noise, and eventually they come together. This is very similar to kind of how AlphaFold used frames. Everybody is disconnected, and they kind of move around independently and then come together eventually to form a nice protein-esque structure. Like I said, diffusion has kind of two processes: the forward noising process, where you take a data example and you iteratively corrupt it such that you eventually get down to a prior distribution that you define ahead of time, in this case, a Gaussian normal distribution. And then you train a model to reverse that process, to create protein-like objects from noise. So at every time step t, we can take a step backwards to t-1 to make it slightly more protein-like. It really just moves each individual residue around such that, yeah, they look more like a protein. RoseTTAFold diffusion is based on RoseTTAFold, which is a structure prediction network. Like AlphaFold, it takes in an input sequence, homologous templates, as well as the initial coordinates or the recycled coordinates when you're doing recycling, and then it takes all that, processes it, and predicts a structure. RFDiffusion takes the RoseTTAFold backbone, fine-tunes it for the diffusion process. So the main differences for this are we no longer have a sequence, everything's masked. We self-condition, so the model makes a prediction of what it thinks the ground truth is, and then we feed that back in and try again. It's very similar in essence to recycling, but it kind of allows the model to look ahead and think about what it thinks about the final structure, and it can kind of maybe adjust what it is thinking in the meantime. And then it's also taking in the diffused coordinates. So at a certain time point, we have a set of coordinates that are slightly noised, or very noised, or like just barely noised, depending on the time step. And then we feed all this in, and then what the model is actually doing is predicting the final structure, what it thinks the ground truth structure is at time 0, which is very similar to what RoseTTAFold is doing as well, which is why this framework is quite successful. Any questions on the overview of RFDiffusion?
What are the initial data for the RFDiffusion below for the diffused coordinates?
Yeah, these are the coordinates of the noisy structure. And then this is self-conditioning information that's essentially a template, but it's like, it makes a prediction, and then you essentially give that prediction back to the model.
Is it in the first step?
In the first step?
Starting, in the first iteration, right?
You don't have it. It could be, so self-conditioning is not always used. When it is used, you make a prediction, you give it back to the model, and then tell it to try again. So in the first step, you would make a prediction, you just give it back to the model.
And the initial coordinates?
Initial coordinates are sampled from a Gaussian distribution. Cool. This is kind of what is happening. So the model itself is given the noisy coordinates, the masked sequence, and then it makes a prediction of what the ground truth is. Initially, it's going to be really bad. It has no idea what we should be looking for in the ground truth structure. However, it can move slightly more in this direction. So what we do is we take a step towards this state, and now we have this. We skip a couple time steps, but yeah. We take this noisy structure now, make another prediction of what the ground truth is, move the coordinates so they're slightly more like this. We keep this process, and as you can see, the noise coordinates are slowly getting more and more, but the ground truth predicted structure is becoming more and more consistent as we go, and the coordinates are slowly being moved in the direction of these ground truth predictions.
Does the model know the prior prediction?
When they're self-conditioning, yes. But only 50% of the time during training, they use self-conditioning. It's just like a regularization way of doing it. Cool. Yeah.
When you say it moves a little bit to what it's currently predicting, how much do the programmers set how much allowed movement there is, or like?
Yeah. So when you're training the diffusion model, you can set a noise schedule ahead of time, and that defines how quickly the data is transformed into uniform noise. There's a similar process in the reverse diffusion, that noise step decreases as the time step decreases. So at first, you're still like adding a lot of noise. It's very stochastic. You don't know exactly where you're going to land. But then as you get closer and closer, you're adding much smaller amount of noise, which allows it to kind of converge to a structure. Yeah.
Where along the process do you have kind of like impose the rules of like, I want it to bind to this interface, or like I want it to contain this key?
Yeah, that's a good question. So we give it to the model pretty much at the start.
Okay.
So you tell it at the start, this is a target protein we want to hold fixed. We want these specific epitopes on it. That information is conditioned into the model. It was trained on that information. So it knows how to use that, and then it'll be able to move the structure over there and bind that.
So that never gets like noise?
No, that information is held constant. It's the conditional information that you give to the model.
So basically the model, so the input is like extended with some coordinates being true all the time?
So if we're doing motif scaffolding or active site scaffolding, or we have a target protein that we're holding fixed, some of those coordinates are held fixed. But if you're like keen-eyed, you can see that the model is still moving those coordinates technically. And you'll see as you're running, it'll have like a ARM-SD value that it prints out that's saying how much the motif is being moved. Typically it's less than an angstrom, it's like 0.2 usually or something like that. But it is slightly moving it, and that's just because the diffusion process can't really hold it fixed exactly. So it is slightly moving.
So like another question to build on that, if we have some true coordinates of like we create a binder, so the protein, one protein is fixed, right? So how is so where is the center of this Gaussian distribution for the coordinates of the thing we're building?
Yeah. So you take your input protein structure, you center it on 0, 0, 0, and then the initial noise distribution is just kind of around 0, 0, 0 as well. And based on the conditional information, it will maybe migrate towards a very specific region in space, towards an epitope or something like that, but it all starts around 0, 0, 0.
And what is the width of the distribution? So like standard deviation for the Gaussian distribution?
I think it's just a standard normal, like just one. So they're like all pretty collapsed, right? Like then they'll spread out.
One like in 1 angstrom?
Yeah, I think it literally 1 angstrom.
Okay. Thank you.
Yeah. Okay, cool. So this is kind of what the model, everything you can do that I've kind of talked about with the model. So you start from random noise, you iteratively take steps. If you have no conditional information, you're doing unconditional generation. You're just generating a backbone that the model thinks is protein-esque. You can also do symmetry, like I mentioned. You take a diffuse structure, symmetrize it. So in this case, this is a C3 symmetry. And every step, you resymmetrize the model so that everything is held symmetric. For the binder target, you give it the target protein you're interested in, and then you start diffusing a binder towards it. Functional motif, you hold the motif fixed, and then you start building something that can scaffold it. And the symmetric motif, you can do something very similar. You hold a symmetric motif fixed, and then you build something that scaffolds that. Here are some results from the model. So as the model is generating structures with more and more amino acids, they tend to be more and more diverse. So for small proteins, you're typically finding a protein in the PDB with a TM score around 0.7. So it is fairly similar to the training data set in the PDB. However, as we're getting more and more residues, it's able to generate more and more diverse structures. When we design the sequences for these backbones and then refold them with RMSD, this is the RMSD design versus AlphaFold2's. So this is the self-consistency. It wasn't called self-consistency at this time, but we've changed. And as we can see, it's pretty good for proteins typically less than 300. Past 300, it starts to kind of grow how reliable the model can refold these backbones. Similarly, they're just really comparing it here to a previously designed message based on hallucination, where you kind of like back propagate information through it and update the sequence. RFDiffusion tends to be better at generating backbones that are designable so that the sequence models like it better. And then they did some ablations. The main idea here is that without pre-computing, so it's kind of this main curve way out here, without using the RoseTTAFold weights, without fine-tuning the model, it does really poorly, training it from scratch. It's a really hard task to learn, but by starting with the RoseTTAFold weights, we're able to really dramatically improve the performance of these models. Yeah, and some of the self-conditioning helped, and yeah. Any questions?
In panel C, RMSD you designed RoseTTAFold2. Is that just using like a simplified model generation, like nothing with like increased seeds or dropout like you can do nowadays?
Right, yeah, this is just unconditional generation, I believe. Yeah.
So like maybe this is premature, but also like if we're creating a binder, could we like specify where exactly we want it to bind and somehow bias the diffusion, so this RFDiffusion probe?
Yeah, so that's like the hotspot residues that we're going to be using. They tell the model that these are the residues at the epitope we are interested in. Make sure to create something that can contact those. It doesn't always listen, but that's kind of the idea. You kind of bias it towards those positions.
How does it work? So how does it bias them?
Well, the model was fine-tuned. So they have a vanilla version of RFDiffusion. Then they took that and trained it with some extra information. In this case, they gave it specific epitope information about which residues it should be binding towards. And then you're able to condition it and retrain, fine-tune the model such that it's able to incorporate that information into the backbones that it's generating. And there's a lot of versions of RFDiffusion that they've fine-tuned. So like you'll see a complex version, you'll see a beta version, so it generates more beta sheets than alpha helices. They've generated a lot of different versions of these weights. We've downloaded a lot of them too. Okay, opening it up a little bit. Like I said, it's very similar to RoseTTAFold. I've already kind of walked through that, and we've talked about how it predicts the ground truth structure from the noise. This is kind of what a single step looks like. They take the current noisy coordinates, they run it through RoseTTAFold, they get the ground truth prediction, and then you interpolate between the ground truth prediction and the current noise coordinates. So that's kind of how we're moving towards the final state. And then there's this little epsilon here kind of indicating that there is still noise being added to it because it is a stochastic process, it's an STE that we're estimating. If we're using self-conditioning, which happened 50% of the time during training, then we take the predicted structure, feed it back in, so now RoseTTAFold gets both the noise coordinates and the initial structure essentially as templates, and then the model tries to repredict what it thinks the ground truth structure is. This is what RoseTTAFold2 looks like. It's similar to AlphaFold2 in the sense that there are kind of three main objects that kind of moving throughout the model. We have an MSA representation, we have the pairwise 2D representation, as well as the coordinate three-dimensional representation of the protein. They kind of just iterate by passing information up and down between these different tracks. It uses attention, similarly to AlphaFold2, but it uses an SE3 transformer, which is an equivariant transformer, that takes advantage of the spherical harmonics that allow it to create equivariant features from coordinates, and then propagate that information to update the coordinates in an equivariant manner. Don't fully expect you to understand all of that, but yeah, that's how they're handling the equivariance part, which is different from how AlphaFold2 was handling it with IPA. Yeah, they have 36 blocks of these, and then finally they throw it through some refinement layers, which are just really the SE3 transformer. There's 4 steps there that finally refine the model at the end. So RoseTTAFold2 was trained to try to bridge the gap between RoseTTAFold and AlphaFold2. So they incorporated a lot of ideas from AlphaFold into the retraining of RoseTTAFold2. So they included the fake loss, which had a pretty good improvement. They also included recycling and distillation and some extra options, and eventually they were able to squeeze out above AlphaFold2 with this model. So they were kind of like introducing a lot of the ideas that AlphaFold2 introduced. They include the triangle multiplication, the recycling and distillation, the FAPE loss. So these are all ideas that AlphaFold2 came up with, and they do seem to be helping a lot. Although the fact that we're able to do this with a completely different architecture means that there's not like something uniquely special about the AlphaFold architecture, which is reassuring. So RoseTTAFold was trained with a variety of different losses. There's that masked language model loss. When we're masking parts of the MSA, we're trying to fill it back in. We had that distogram loss, so it predicts a distogram based on that pair representation. It has the FAPE loss, which is really just making sure that those frames are aligned properly, and then all the coordinates around it. It's also predicting torsion angles, so it's predicting the chi angles for the side chains. We also have an accuracy term for the confidences, and then the experimentally resolved term. They also do some fine-tuning steps where they introduce a couple extra losses, including a bond angle and length loss and Vater wall interaction loss, which is kind of cool too. This is one of the few models that I've seen to use like a very physical term like Vater walls, which is cool to see. When they fine-tuned RoseTTAFold for RFDiffusion, they have two main losses. They have this L frame and this L2D. So when they're predicting these structures, they had that pair representation. From that pair representation, they're predicting a bunch of different values that really represent 6 degrees of freedom between two residues. And these are all kind of coming from, they originally came from like Rosetta, TR Rosetta, which is what TR Rosetta was predicting in the end. So these are pretty much just 6 degrees of freedom between two residues, so it counts, I think it's a distance and maybe an angle and two dihedral. I don't remember exactly, but oh yeah, so distance, dihedral, and a regular angle. Those are the 6 degrees of freedom. And then the frame loss is really just computing the difference between the ground truth structure and then the predicted ground truth structure. And we have this weighted variable that kind of helps balance out the different time steps that we're at. So like when it's at a very high time step, it's going to be very wrong mostly. We don't want that to really dominate the model performance. We want it to still do well at the low time steps too, where the error is probably going to be a lot less. The deframe is really just comparing the translation components and the rotation components of the frames. Something that interesting that I want to note is that this isn't a proper diffusion loss. This is more of a heuristic, but it works really well still. And I think that kind of just shows that maybe the theoretical diffusion-based losses aren't required, and we can still make simplifying assumptions, which was also kind of supported by some of the other diffusion papers that were coming out around the time. Like I mentioned, there are a lot of different versions of RoseTTAFold diffusion. We have the based version, which was just trained on monomeric structures, and it's really used for unconditional generation and motif scaffolding. So those are the two tasks that it was used that it was trained on. They also trained another model called the active site model. They started from this base version of the model. They trained it on both these two tasks here, as well as a triple contact task, where they held 3 residues fixed, and then told it to scaffold around those residues and fill in the rest of the protein. They also have a version of the PPI model, where they also started with the base, but then they trained it on monomers and complexes, and they also added some additional tasks where parts of the target protein were seen. So you all either saw parts of the secondary structure, you saw the block adjacency matrix, so maybe how the secondary structures are composed relative to one another, and then you also maybe saw some hotspots biasing the model towards specific epitopes of the target protein. And then finally, they also have this in-paint-seq model, where monomers and it was trained on monomers and complexes, but some of the motif residues are masked sequence identity. So when we're doing this, whenever it saw part of the protein, it still saw the sequence associated with that part of the motif or the target protein. So it could still kind of take into account what chemical composition is at that epitope or part of that target protein or that motif. In this case, maybe we want to have the same structure of the motif, but we don't want to have that sequence that was associated with it at the original structure. So here we can in paint kind of like imagine what could be there as we're diffusing. So maybe it biases the model towards something that can be a little bit more generalized or can handle different sequences. No. Okay. Another thing I want to talk about is potentials. These are ways to guide the generation process. This is also called conditional information, conditioning, lots of different ways to do it. Potentials is kind of a abuse of jargon, but we'll go with it because everything in the code is also saying potentials, but that's fine. So the whole idea here is this is the regular sample function. So for every time step, we throw it through RFDiffusion and get the ground truth predicted structure. Then we take a step towards that ground truth structure. We have our updated noisy structure, and then we hold on to the previous one. This is a self-conditioning. So we do self-condition when we do sampling. We explicitly do that, even though it was trained 50% of the time. When we're doing guided sampling, we also have this extra term that we use to bias that update step. So we include a potential that operates on the noisy coordinates, and then we have a scale that kind of determines how big of a step we make based on that potential. The potentials are just differentiable functions that are based on the noisy coordinates, and they can help bias the model towards predicting something that is more of use to you. For example, you might want to restrict the radius of gyration of a protein. So if you're getting a lot of these elongated alpha helices, that's going to have a really high radius of gyration. You want to typically minimize that because proteins don't have super elongated structures a lot of the time. And then if you include that, that'll kind of make it more of a compact, more globular structure. There's also potentials for number of contacts. So if you want to increase the number of contacts with a substrate or within the protein itself, there's intra-chain contacts, inter-chain contacts. So intra is within the same protein, inter is between protein chains, and then you also have the substrate contacts. So these are just different ways to bias the generation process, but it's also pretty easy to implement your own if you have an idea that isn't incorporated by these. I've done it a few times, so it's really not that bad. A couple limitations. It can produce overly loopy or extended structures. I think the typical way to kind of avoid this is either generate a lot of things and throw out the things that are bad, or use a potential to help bias the generation towards something that is more useful. Another limitation, it just can't handle other molecules. That's just kind of a limitation of RoseTTAFold2, which was addressed in RoseTTAFold All Atom, which RFDiffusion All Atom makes use of. And then I just wanted to talk about, I think, this one extension, which is pretty much just RFDiffusion, but it's also doing sequence diffusion at the same time. So it's simultaneously creating a sequence to go along with the backbone that it's generating as well. An interesting caveat, well, okay, so yeah, it generates a sequence, but you could also do sequence-based guidance, so you can guide it towards a very specific amino acid composition, maybe a net charge, hydrophobicity, predicted activity, stuff like that. So it's another way of biasing the generation process, but now in sequence space. I think an interesting caveat with these joint diffusion models is a lot of the time people don't tend to use the sequence that comes out of them, but they like redesign the sequence with like protein MPNN or ligand MPNN. But interestingly, they're more the backbones tend to be more designable if you're jointly diffusing the sequence and the backbone. So just some weird like nuances with these kind of models. I don't think we fully understand why that's the case yet.
Can you expand a little bit on what you mean by designable? So you said when you're co-diffusing the sequence and the struct and the backbone at the same time, these tend to be a little more designable. I'm just having a hard time understanding what that means in practice.
Yeah, so when I said designable, I mean if you generate a sequence for that and then refold it, it looks like that designed to backbone.
Okay.
So can you do something like Minecraft with RoseTTAFold then? Same nature, where you propagate the gradients up to the sequence?
You can do that with like RoseTTAFold2 if you wanted, or RoseTTAFold All Atom. That's totally possible because like they're pretty much the same thing as AlphaFold, and if you just backpropagate, you could totally do that.
You do it as well, like in every step that you go through it, then you're generating the sequence and the backbone at the same time, right?
Yes. I don't know how like useful it is to backpropagate through like a diffusion-based model, but at least the structure prediction models are would be easier to do because there's not like a multi-step process. It'd be a little tricky with one of these.